In this video, I want to talk about applying the idea of integration to work. And what is work? Work is a physical concept, and we don't want to get into the physics too much of it, but we're thinking of it as some force applied over some displacement. The whole idea is how much force we've applied to move something from one location to another in kind of a displacement fashion, not a distance fashion. If we move an object from place A to place B and then move it back to place A, we think of that as doing no work because it ended up back at the same location. So we're kind of interested in a displacement rather than a distance here. And the whole idea is that if we have a graph, and this graph is going to be force on the y-axis and displacement on the x-axis, and we graph the force we applied to some sort of object to move it from one location to another, then the work done is going to be the area under this graph. And when we're starting to think area under a graph, we're starting to think integration. And that kind of makes sense too. If you have, using the idea of Riemann sums, well, maybe we want to see how much work we did over 1 unit here. So let's say this here is 1 meter. Let's say we're in meters. Then we can estimate the work done by this rectangle here, right? This right-hand rectangle where we're taking the height of it to be the function value at the right end point of this rectangle. And this is the exact same idea as Riemann sums. We kept going. We could approximate the work done across the entire interval here. And to get a better approximation, we just reduce the width of our integrals towards infinity. And more formally, and in terms of integration, if we have a force function applied over some sort of displacement, well, the work is going to be the integral of that force function from location A to location B. So that's what's going on here. And let's just do a quick example to kind of see how this goes. So let's say we indeed have a force function, and it is x times e to the x squared, and it's acting on some particle as it travels from 0 meters to 1 meter, and we want to know what's the work done to this particle. And I think it's instructive. I'll leave you guys to go into Desmos or something similar and just see a graph of what's going on. So that's my suggestion. First, maybe pause the video and graph this. You could try to sketch it yourself if you like, or put it in Desmos and see what the force displacement graph would look like, and just to get a flavor for the amount of work done. Okay, now that you're back, well, we're setting this up as a work problem, so it's going to be the integral from the starting location to the end location of our force function here. Now I'm missing a dx, so let's put that in just to make sure we know what variable we are indeed integrating over. And we've translated our problem into the language of integration, so now we just go to our bag of tricks of integration. How do we integrate this? Well, I see that we have a function here, x squared with its derivative multiplied by that kind of composed function. So we're good to go with a u substitution. So let's do that. So u is going to be x squared, and du is going to be 2x dx. So let's multiply our integral by 2 over 2, so we can take out that 2x dx and replace it with du. So that's a nice little substitution. We'll take out the x dx and the 2, and the x squared will become that u. So what do we have here? We have 1/2, and I'll fill in the bounds in a second, the integral of e to the u du, which we know, that's nice and easy. And let's figure out our bounds here. So, all right, when x equals 0, u equals 0 squared, which is still 0. So our bottom number there is 0, our lower bound for integration. And when x equals 1, similarly, u equals 1 squared, which is 1. So we're going to integrate over 0 to 1, just like up here. So let's go ahead and quickly do that. I don't think there's too much to write down, since the antiderivative of e to the u is just e to the u, and we're going to evaluate that from u equals 0 to 1. And we still need that 1/2 as well. So we'll put that 1/2 in front. And that simplifies to e minus 1 over 2. And work is done in joules, or Newton meters, if you will. So it's e minus 1 over 2 joules of work done. Okay, let's look at another example here. And this involves Hooke's law of springs. So let me tell you what's going on here. So the idea is that the force required to maintain a spring stretch out x meters from rest is proportional to its displacement. So the force required is some constant called the spring constant times the amount you're stretching the spring out from rest. And just to be clear, this doesn't hold for all x, but as long as x isn't too large, as long as you're not stretching the string or the spring an incredible amount, this will hold. So let's look at our example here. We know that a force of 60 newtons is required to move a spring from 40 centimeters long, which is its rest point, to a length of 55 centimeters. So we want to know, first of all, how much work was required to move the spring. And then we want to know, well, how much work is required to move the spring an additional 5 centimeters from 55 to 60. And here's a little diagram of our situation. There's our spring at rest. And we want to stretch it, first of all, for part A, we want to stretch it an additional 15 centimeters so that we're at 55 centimeters. And then part B, we want to stretch it an additional 5 centimeters. Now remember that the rest point is 40 centimeters. So we're thinking of this point here as kind of our origin. This is when the displacement is 0, is when the spring is 40 centimeters long. So be careful about that. So I think it's a good idea to pause the video now and try and set up solving this problem, A and B. Remembering that when the spring is 40 centimeters long, it has a displacement of 0, and we care about the displacement. Okay, now that we're back, here's our force function that was given to us in the question. It's just the spring constant times the displacement. And we know that indeed it took 60 newtons of force to stretch the spring 15 centimeters. Remember, this unit is Newton meters, so we need to make sure that we're converting our displacements here to meters. So that's 0.15 meters. And we can solve for K here. This just tells us that K must be 400. And by dimensional analysis, you can see that the units here is going to be newtons per meter. So that's our spring constant there. So we have our spring constant, so now we can set up our integral entirely. So we want the work done. Now remember, we're going from 40 to 55, but 40 is the length of the spring itself, so that's at 0 displacement, and we want to stretch it 15 centimeters. So we know our force function itself is big F of x is 400x. So that's going to be what we're integrating from 0 to 15 centimeters, or 0.15 meters. And we do that via the reverse product rule, and we get 200x squared, which we want to evaluate from 0 to 0.15. Plug that in, and you find that you've done 4.5 joules of work. Now for part B, we want to stretch it an additional 5 centimeters. So now we're starting at 0.15 and we're going to 0.2. Because remember, the spring is at rest at 40 centimeters. So we're stretching it from 0.15 to 0.2. And we already know the antiderivative to this. We don't need to do the work again. That's 200x squared, which we're going to evaluate from 0.15 to 0.2. And if we do so, we indeed get that we have done 3.5 joules of work. Another nice application of integration has to do with the average value of a function on an interval. If we look at our diagram here, we can see that, hey, functions vary. They're larger in some places than others on some interval, as long as our function is continuous. This is very kind of nice, a nice situation. But we want to think of some average function. What do we mean by an average function? Well, we have to kind of define what we mean here. And thinking about the average of numbers, or the mean of numbers, as a model, well, we can say, well, the area under this curve here is the same as if we kind of shared that area fairly across the entire interval from A to B. So that's what we kind of mean by the average of a function. So if we took the area under that function and we shared it fairly across the entire interval, so it's a nice uniform flat line here, what would that value C be? So that's our idea here. If we have the average value of a function f of x on some interval from a to b, it's that value c, where if we take the integral from f of x from a to b, that's the same thing as the area under this rectangle. So the area of the integral of c from a to b. Remember, c is just some number. And this is very easy to integrate. You could either integrate this itself, or just realize that if you're integrating any sort of number, well, that's just a flat function with no slope. It's just a horizontal line from a to b. So it has height c and width b minus a. So the area under that is b minus a times c. So that's what we know. And if we're looking to find this c, well, let's just divide both sides by b minus a. So there we go. That value c, that average value of our function, is just the integral of our function between a and b divided by the length of our interval, b minus a. So the average over this interval is the integral divided by the length of the interval. Great. Okay. So, let's try this. Let's find the average value of this function. This one kind of looks complicated. X times sine of ln of x squared plus 1 over x squared plus 1 from x equals 1 to 4. And again, maybe it's a good idea to graph this in Desmos or something like that, whatever program you like. Maybe try and graph it by hand first, just get an idea what it looks like. But I'll just do a little bit of a sketch here. So there's our axis, and we want from 1 to 4. And it looks something like this. So it looks something like that. Just to put in some values, this is about 0.31. This is about 0.08, something like that. Actually 0.07. And finally, let's just put in that maximum. It's at 1.605 and about 0.43. So that's kind of what this function looks like. And, well, if we wanted an average function, we kind of want the place where it looks like an area of a rectangle would have the same area. So let me kind of sketch something. So maybe something like that wouldn't be bad. Where, well, this area that overshoots the rectangle, maybe it's a little bit bigger than the area here, where the rectangle is larger than the function. So something like that. This isn't a perfect sketch, but we're looking for a value c around there. So we're thinking maybe I made it a little too low here, but this value c, it looks like, well, maybe somewhere just above 0.3 would be a reasonable guess. Something like that. Again, it's tough to say. This is only a sketch too. Let's see what it works out to anyway. But we know for sure that c is going to be less than the maximum, which is 0.43, and greater than the minimum, which is 0.07. So at least we have a place to start. And again, this function c, or this value c, I guess, is going to be 1 minus the length of our interval, 4 minus 1, times the integral from 1 to 4 of our function, x sine ln of x squared plus 1 over x squared plus 1 with respect to x. Now, we've converted our idea here into the language of calculus. So maybe it's a good idea, pause the video now, see if you can take this integral and find this value c, and see if it matches up roughly with our diagram here. Okay, now that we're back, let's look at this interval, or this integral. And we see this looks, there's a lot of pieces to this, so it's a bunch of compositions and a bunch of things multiplied together. So we have x times this kind of triply nested composition sine of ln of x squared plus 1 over x squared plus 1. I see some composition of functions. I'm thinking that a good idea might be to do a substitution. So I'm going to look around, and I see that if I let u equal ln of x squared plus 1, then its derivative is going to be 1 over x squared plus 1 times the derivative of what's on the inside. So that would be 2x. And there's that extra x. So it looks like we can just take care of all of this here just by making a nice substitution. It turns out this isn't particularly hard at all. It just looks difficult. So let's let u equal ln of x squared plus 1, and then du is going to be the derivative of this dx. So the derivative of a ln of x squared plus 1 is going to be 1 over that, 1 over x squared plus 1, times the derivative of the inside function, just using the chain rule, so that's going to be times 2x, and that's with respect to x. So that's great. Let me rewrite it, I guess, as 2x over x squared plus 1 dx. So again, we can take out this x and this x squared plus 1, and, well, let's multiply the function by 2 over 2, so we can take out this 2 here. So we'll take out all of that and replace it by du, and then we're left with just, well, we're replacing this x squared plus 1, or this ln of x squared plus 1, by u. So actually this looks quite simple, and we'll worry about the bounds of integration in a second. So this becomes, well, here we have 1/3 times a half, since we took out that 2, so that is 1/6 on the outside, times the integral. Again, we'll worry about the bounds in a second. All of that red stuff is substituted out for du, and we're just left with sine of u. That's great. So let's figure out what our bounds are. So when x is 1, u is ln of 1 squared plus 1, which is ln of 2. And when x equals 4, u is ln of 4 squared plus 1, which is ln of 17. And I won't approximate those. I'll just leave them as ln of 2 and ln of 17. Doesn't really matter. So our lower bound is ln of 2, and our upper bound is ln of 17. Okay, that is fantastic. So let's do this integral. Well, the antiderivative of sine of u is negative cosine of u. That's nice and easy. And we're going to evaluate that from u equals ln of 2 to ln of 17. What you could do instead, some people like to do this instead of figuring out the bounds of integration. They'll just put in x equals 1 and x equals 4 here, just not resubstituting these guys. And then down here, they'll write it in terms of x. So x equals 1 and x equals 4. And then resubstitute u in here. So we know u is ln of x squared plus 1, so they'll write this as negative cos of ln of x squared plus 1, and just kind of fill it in from there. But both ways are equally as good as each other. But it's fairly easy to just kind of figure out your bounds once you know your substitution. So I just like doing it like this, just substituting as we go with everything. Okay, so let's go ahead and just write down our final answer. So this is 1/6 times negative cosine of ln of 17 minus a negative, so plus cosine of ln of 2. And that's it. And to give an approximation of that, we get that indeed this c value here, since that's what we're solving for, is 0.287, which isn't too far off from our guess. Again, this is just a sketch of the graph anyway, but it seems to kind of jive with what we expect it to be, kind of around this left end point here, since we go up and then we go down. So that's great. And a good question is, well, does this value c always exist? And the answer is yes, as long as your function is nice and continuous. So as long as f of x is continuous. And we will indeed show this. I like proving why things are true. And in fact, this is called the mean value theorem for integrals, which basically says exactly what you think it would say. We're looking for some sort of average value of a function. We might as well call it the mean value. So the mean value theorem for integrals. And it says, well, if we have a function that's continuous on some interval here from a to b, then there's this value c. That's the mean value or average value of that function in the way we just defined it. So let's prove this, and I'm not going to do the proof in all its glory. I'm just going to kind of sketch out what's happening here, and we're going to set up some notation here. So I'm going to call big M the maximum function value on this interval a to b, and we know there is a maximum value since our function is indeed continuous. We have this extreme value theorem, which tells us if we have a continuous interval, well, there must be a maximum value, and analogously, there must be a minimum value, which I'm going to call little m is going to be the minimum value on this interval. It doesn't go off to infinity or no weird stuff happens. I know I have indeed a maximum and minimum value since my function is continuous on this nice closed interval. So what does that give me? Well, it says that this integral here must be between little m times b minus a and big M times b minus a. And let me kind of explain why. So if we have our function, let's say our function is in blue here, have it something like that. There's our a, and there's our b. Well, our maximum value is here, and our minimum value, which I'll do in green, is there. So our minimum rectangle obviously underestimates our area, and our maximum rectangle obviously overestimates our area. So we have that indeed this integral is squeezed between the minimum and the maximum rectangles here. And we'll also say, just to give it a little more notation, this maximum value, let's say this occurs at x sub big M, and this minimum value occurs at x sub little m. So we can say, just as an example, this is saying that f of this x value is our maximum, and f of this x value for our minimum gives us our minimum. That's what I mean there. Okay. And the whole idea here is that we are dealing with a continuous function. So we know that, well, we have this kind of maximum value at x big M and this minimum value at x little m. We can use the intermediate value theorem here, and that's the key. We want the value, and we're going to think of the area. We know there's some value here that's going to be between the area of the maximum rectangle and the area of the minimum rectangle. So there's going to be this value k. That's going to be the area that we want. And that's going to be that value we're looking for, that mean value of our function. So what is that? We know that there has to be some xk, and we're thinking this k, we want this to be our mean value. So we're thinking of this as our c here. We want this to be c. But this will hold for any k that's between our minimum and maximum value. So again, let me sketch the function again. So there's our maximum value, there's our minimum value. So I should use a little m for minimum, of course, my mistake. So any k in here we can find an x value that attains that xk. So if we wanted, say, this k, then we know there's an x value that attains that. So when we plug that in, if we plug xk into our function, we indeed get k. We know one exists. And so Well, just rearranging that equation on the previous slide, we can find the value, the integral of our function divided by b minus a, since, just dividing that previous equation by b minus a, we get that our minimum is less than or equal to this integral over b minus a, which is less than or equal to our maximum. So this value is between the minimum and the maximum. We want that to be our average value. So that's in our interval from m to m, since it's between them. That's great. So we'll use the intermediate value theorem, and that xk is going to be our value, and k is going to be indeed our average value of our function on the interval. So that's what's going on here. So we can always find it using the intermediate value theorem to help us out. Let's look at one more example. So let's say in Vancouver, we have the temperature on some day. In fact, that day will be May 1st in our example. There's a function that represents the temperature, and that is 18 plus 7 times sine of pi t over 12, where t is number of hours after 9 a.m. So if t equals 0, that's a temperature exactly at 9 a.m. If t equals 3, that's a temperature at noon. If t equals -1, that's a temperature at 8 a.m. on May 1st. So this is the function here. And we're looking for the average temperature during the period from 9 a.m. to 9 p.m. So what are we looking for here? Maybe pause the video, see if you can write down the integral expression in order to find this average value. Okay, now that we're back, we want this average value c. It's going to be 1 over the length of our interval. And from 9 a.m., that's when t equals 0. 9 p.m. is 12 hours later, so that's when t equals 12. So it's going to be from 12 minus 0, or 1/12, times the integral over that region from 0 to 12 of our function. 18 plus 7 sine pi t over 12 dt. And then it's just a matter of simple integration here. So let's break this up maybe into some pieces. So we'll take the 1/12 out, or leave the 1/12 out, I should say. And then we have the integral from 0 to 12 of 18 dt plus 7 times the integral from 0 to 12 of sine of pi t over 12 dt. Okay. And from here, the first part's pretty easy. So we have 1/12 times the integral. So this is going to be 18x is the antiderivative of 18, evaluated from x equals 0 to 12. So that is the first bit. Maybe I'll make this a straight line so it doesn't look like, so I don't get it confused, I guess, with our square bracket out here. And then plus 7 times this integral here. So let's do a little substitution. U is going to be pi t over 12. So du is going to be pi over 12 dt. So I need to take out a pi over 12, or you can even rearrange this and say that, well, 12 over pi du equals dt. So we can look at our substitution like that. So we're going to replace that dt with 12 over pi du, and that's fine. So let's go ahead and do that. So we have 7 times 12 over pi. Let me put a times there so it doesn't look like a mixed number. Times the integral. And we'll worry about the endpoints in a second. No big deal. Of sine of u du. And that's going to be 1/12 times, well, 18 times 0 is 0, so it's just 18 times 12. I'll just write it as 18 times 12 for now. We can calculate that in a little bit. Plus, well, 84 over pi times this integral, which is going to be negative cosine of u. And that's right, I have to put in my bounds here, so let's figure out the bounds. So when t equals 0, we have that u is pi times 0 over 12, which is 0. And when t equals 12, u is pi times 12 over 12, which is just 1. So this is indeed the integral from 0 to 1. So this is going to be negative cosine u evaluated from u equals 0 to 1. So that's just going to be negative cosine of 1 minus negative or plus cosine of 0. So I'll leave you calculate that. And you should get, if you calculate this, 18 plus 7 over pi. You'll see that those 12s cancel quite easily with the 1/12 outside. And we got 20.228 degrees Celsius is the average